A Bernoulli differential equation is a first-order ODE that looks almost like a linear equation, but has an extra power of the unknown function y. The generic standard form is dy over dx plus p of x times y equals q of x times y to the n, where p of x and q of x are ordinary not necessarily constant functions of the independent variable x, and n is any real number. The key to spotting a Bernoulli equation is the presence of y raised to a power n on the right-hand side, while the left-hand side contains the usual linear combination of y and its derivative. If n equals 0 or n equals 1, the equation becomes linear, but for any other n, it is non-linear yet still solvable with a simple change of variables. Think of the equation as a mixed-gear bicycle. Most of the chain runs straight linear part, but a single gear y to the n term changes the speed in a predictable way that we can re-gear to make the whole ride smooth. The trick to solve a Bernoulli equation is to turn it into a linear one by a clever substitution. Define a new variable v as v equals y to the power of 1 minus n. Why this works can be seen by differentiating v with respect to x using the chain rule. dv by dx equals 1 minus n times y to the negative n times dy by dx. Now solve the original Bernoulli equation for dy by dx and replace dy by dx and y to the negative n with expressions in v and dv by dx. After some algebra, you obtain dv by dx plus 1 minus n times p of x times v equals 1 minus n times q of x. This is a linear first-order ODE in v because v appears only to the first power and there is no product of v with its derivative. The substitution is like changing the units on a measurement stick. You replace a tangled combination of y and y to the n with a single straight line variable v, making the problem easier to walk through. Once the equation has been rewritten as dv over dx plus m of x times v equals n of x, where m of x equals 1 minus n times p of x, and n of x equals 1 minus n times q of x. We solve it with the integrating factor method, the workhorse for any linear first-order ODE. The integrating factor mu of x is defined as mu of x equals exponential of the integral of m of x with respect to x. Multiplying the whole ODE by mu of x gives mu times dv over dx plus mu times m times v equals mu times n, which becomes the derivative with respect to x of mu times v equals mu times n. Now integrate both sides with respect to x mu times v equals the integral of mu times n with respect to x plus c. And finally solve for v of x equals 1 over mu of x times the integral of mu of x times n of x with respect to x plus c. The integrating factor acts like a lubricant that turns the left-hand side into a perfect derivative, so you can simply undo the derivative by integrating. This step is routine, but remembering to compute mu correctly, especially the sign of the exponent, saves a lot of algebraic headaches. After we have v of x from the previous step, we must remember that v equals y to the power of 1 minus n. Solving for y gives y of x equals v of x raised to the 1 over 1 minus n. If the problem supplies an initial condition such as y of x sub 0 equals y sub 0, we substitute x equals x sub 0 and y equals y sub 0 into the expression for v to find the constant c that appeared after integration. v of x sub 0 equals y sub 0 to the 1 minus n equals 1 over mu of x sub 0 times the integral from unknown to x sub 0 of mu n dx plus c. Solve this equation for c, then plug it back into the formula for v of x, and finally raise to the power 1 over 1 minus n to obtain the explicit solution y of x. For boundary value problems, values given at two different x, you may need to solve for c using both conditions, which sometimes leads to a system of equations. The overall picture is similar to assembling a puzzle. You first solve a simpler picture v, then translate the pieces back to the original picture y and fit the given edge pieces, initial and boundary data. Explanation: when n equals 0, the Bernoulli equation becomes dy over dx plus p of x times y equals q of x times y to the 0 equals q of x, which is simply a linear first-order ODE. No substitution is needed. You can go straight to the integrating factor method with m of x equals p of x and n of x equals q of x. When n equals 1, the equation reads dy over dx plus p of x times y equals q of x times y to the 1 equals q of x times y. Subtract q of x times y from both sides to obtain dy over dx plus p of x minus q of x times y equals 0. Again, a linear homogeneous equation. In both special cases, the power term disappears or merges with the linear term, so the extra Bernoulli machinery is unnecessary. Recognizing these shortcuts early can save you minutes on an exam. You simply treat the problem as a standard linear ODE. A useful analogy is a machine with a gear that can be either engaged and not equal to 0 or 1, or disengaged n equals 0 or 1. When disengaged, the machine runs in a straight line requiring only the basic tools. When engaged, you need to change the gearing, the substitution, to keep it moving smoothly. Explanation: let us solve the concrete example dy over dx plus 2 over x times y equals x cubed times y squared. Here p of x equals 2 over x, q of x equals x cubed, and n equals 2. Step 1: substitution. Set v equals y to the 1 minus n equals y to the minus 1. Then y equals 1 over v and dv over dx equals negative y to the minus 2 times dy over dx equals negative 1 over y squared times dy over dx. From the original ordinary differential equations, solve for dy over dx dy over dx equals x cubed times y squared minus 2 over x times y. Multiply by negative 1 over y squared to get dv over dx dv over dx equals negative x cubed plus 2 over x times 1 over y equals negative x cubed plus 2 over x times v. Rearrange colons. dv over dx minus 2 over x times v equals negative x cubed. Step 2: linear form. This is linear in v with m of x equals negative 2 over x and n of x equals negative x cubed. Step 3: integrating factor. Mu of x equals exp of integral of negative 2 over x dx equals exp of negative 2 ln absolute x equals x to the minus 2. Multiply the equation by mu x to the minus 2 times dv over dx minus 2 over x times x to the minus 2 times v equals negative x cubed times x to the minus 2, which gives derivative with respect to x of open bracket x to the minus 2 times v close bracket equals negative x. Step 4: integrate. X to the minus 2 times v equals negative integral of x dx plus c equals negative 1/2 x squared plus c. Solve for v v equals x squared times open parenthesis c minus 1/2 x squared close parenthesis. Step 5: return to y. Remember v equals y to the minus 1, so 1 over y equals x squared times open parenthesis c minus 1/2 x squared close parenthesis. Therefore y of x equals 1 divided by x squared times open parenthesis c minus 1/2 x squared close parenthesis. Step 6: apply an initial condition if given. Suppose y of 1 equals 2, then 2 equals 1 divided by open bracket 1 squared times open parenthesis c minus 1/2 times 1 squared close parenthesis close bracket, which implies c minus 1/2 equals 1/2, so c equals 1. Thus the particular solution is y of x equals 1 divided by x squared times open parenthesis 1 minus 1/2 x squared close parenthesis. The whole process mirrors changing a bike's gear substitution, lubricating the chain integrating factor, and finally riding with the correct speed final y. Examiners love to test whether you can spot the Bernoulli form quickly, and whether you remember the substitution v equals y to the 1 minus n. Common pitfalls include forgetting the sign when differentiating v dv by dx equals 1 minus n times y to the minus n dy by dx. A missed minus sign flips the whole linear equation. Mixing up p of x and q of x. Always keep the original equation in the shape dy by dx plus py equals qy to the n before substituting. Using the wrong integrating factor. The factor is exp of the integral of open parenthesis 1 minus n close parenthesis p dx, not just exp of the integral of p dx. not simplifying the linear ODE. After substitution, you often get terms that cancel. Write them clearly to avoid algebraic clutter. Skipping the step of returning to y, many students stop at v of x and forget to raise it to the power 1 divided by open parenthesis 1 minus n close parenthesis. Time-saving shortcuts. Check n first. If n equals 0 or 1, skip the substitution entirely. Write a template. Keep a short note on your scratch paper with the 3-step template substitution to linear form to integrating factor. Fill in p, q, n, and you are done. Memorize the integrating factor formula for Bernoulli. Mu equals x to the open parenthesis 1 minus n close parenthesis integral of p dx when p is a simple power of x. This lets you write mu instantly. Use symmetry. If the ODE is homogeneous in powers of x and y, you can sometimes guess the solution shape. For example, y equals k divided by x before full work, then verify. These habits cut down on careless algebra and let you finish the question within the tight exam window. Problem 1. Solve dy by dx plus 3 over xy equals x squared y to the 4th, with y of 1 equals 1. A solution sketch. Identify p equals 3 over x, q equals x squared, n equals 4. Substitution. V equals y to the 1 minus 4 equals y to the minus 3, implies dv by dx equals minus 3y to the minus 4 dy by dx. From the original equation, dy by dx equals x squared y to the 4th minus 3 over xy. Multiply by minus 3y to the minus 4. dv by dx equals minus 3x squared plus 9 over xv. Linear ordinary differential equation. dv by dx minus 9 over xv equals minus 3x squared. Integrating factor mu equals exponential of the integral of minus 9 over x dx, which simplifies to x to the minus 9. The derivative with respect to x of x to the minus 9v equals minus 3x to the minus 7. Integrate x to the minus 9v equals 3 divided by 6x to the minus 6 plus constant, which is 1/2 x to the minus 6 plus c. Solve for v. V equals x to the 9 times parentheses 1/2 x to the minus 6 plus c right parenthesis, which simplifies to 1/2 x cubed plus c x to the 9. Return to y. Y to the minus 3 equals 1/2 x cubed plus c x to the 9. Therefore y equals bracket 1/2 x cubed plus c x to the 9 bracket to the minus 1/3. Apply the initial condition y of 1 equals 1. 1 equals bracket 1/2 plus c bracket to the minus 1/3. So 1/2 plus c equals 1, giving c equals 1/2. Final solution. Y of x equals bracket 1/2 x cubed plus 1/2 x to the 9th bracket to the minus 1/3. Problem 2. Given dy by dx minus 4y equals e to the 2x times y cubed. Find the general solution. A solution sketch. Write in standard form, dy by dx plus negative 4y equals e to the 2xy cubed. Thus p of x equals negative 4, q of x equals e to the 2x, n equals 3. Substitution. V equals y to the 1 minus 3 equals y to the minus 2, which gives dv by dx equals minus 2y to the minus 3 dy by dx. Solve for dy by dx from the original equation. dy by dx equals 4y plus e to the 2xy cubed. Multiply by minus 2y to the minus 3. dv by dx equals minus 8y to the minus 2e to the 2x. Since v equals y to the minus 2, the term minus 8y to the minus 2 becomes minus 8v. Linear ordinary differential equation. dv by dx plus 8v equals minus 2e to the 2x. Integrating factor mu equals exponential of the integral of 8 dx, which is e to the 8x. The derivative with respect to x of e to the 8x times v equals minus 2e to the 10x. Integrate e to the 8xv equals negative 2 divided by 10e to the 10x plus constant, which simplifies to negative 1/5 e to the 10x plus c. Solve for v. V equals e to the minus 8x times bracket c minus 1/5 e to the 10x bracket, which simplifies to c e to the minus 8x minus 1/5 e to the 2x. Return to y. Y to the minus 2 equals c e to the minus 8x minus 1/5 e to the 2x. Hence y of x equals bracket c e to the minus 8x minus 1/5 e to the 2x bracket to the minus 1/2. Problem 3. Show that the equation x dy by dx plus y equals x squared y squared can be reduced to a separable form without using the Bernoulli method, and solve it. A solution sketch. Divide by x not equals 0. dy by dx plus 1 over xy equals xy squared. Recognize a Bernoulli equation with n equals 2, but we seek a separable form. Rewrite as dy by dx equals xy squared minus 1 over xy, which factors as y times parentheses xy minus 1 over x parentheses. Let u equal 1 over y, which gives du by dx equals negative 1 over y squared dy by dx. Substitute the expression for dy by dx from above. Du by dx equals negative 1 over y squared times bracket y times parentheses xy minus 1 over x parentheses bracket, which simplifies to negative parentheses xy minus 1 over x parentheses over y. Since u equals 1 over y, we have y equals 1 over u. Therefore du by dx equals negative left parenthesis x divided by u minus 1 divided by xu right parenthesis, which simplifies to negative x over u plus 1 divided by xu. Multiply both sides by u. U du by dx equals negative x plus 1 over x. This equation is separable. U du equals left parenthesis negative x plus 1 over x right parenthesis dx. Integrate 1/2 u squared equals negative 1/2 x squared plus the natural logarithm of absolute x plus constant. Replace u with 1 over y. 1/2 times left parenthesis 1 over y squared right parenthesis equals negative 1/2 x squared plus ln of absolute x plus c. Solve for y. Y squared equals 1 divided by left parenthesis negative x squared plus 2 ln of absolute x plus c prime right parenthesis, where c prime equals 2c. Therefore y of x equals plus or minus 1 divided by the square root of left parenthesis negative x squared, plus 2 ln of absolute x plus c prime right parenthesis.